All right, so this is lecture number 5, Data Science for Business, and we're going to talk about classification today. We're going to talk about, CRM, as customer relational management, and we'll talk about churn prediction modeling. So that's the plan. Now, before we go into that topic, I want to spend a few minutes discussing the results of the poll that we have done, and thanks a lot to those who participated. If you did not, well, that was your actually chance to influence our course, right? And we'll try to listen to you on this one. We'll have another poll at the end of the course. Hopefully you will participate. So for right now, we got like 61% response rate, which is sort of okay-ish. What do we see? Well, I'll go over lectures and seminars. Overall sort of, lecture difficulty is actually on the lighter side, right? So, like 30% believe that they can be harder. And in fact, some of the written comment on, asking guys for me to go deeper into, business side of things, or maybe something that's not taught in other machine learning courses. Okay, we'll, in the last, 2-3 lectures, we'll pay more attention to business side of things. Lecture is quite interesting and, understandable. So again, for lectures, we'll probably shift them a little bit, make them a little more, complicated, I would say, a little bit more challenging. Seminars, it seems like, seminar material is well balanced. The interest is all over the place. That's probably due to, again, very strong focus of seminars on RapidMiner. But we're doing it for those of you who actually, never done programming. Now, where we really need to pay more attention for us is homework assignments, where we see that a lot of people think that this can be done better, and we'll need to provide a bit clearer formulations and make sure there is enough clarity within the homeworks, right? And so we'll take this into account, we'll work on it. The good news that in spite of homework maybe sometimes not being extremely clear, you still feel that your work is assessed fairly, which is good. RapidMiner, again, the response is all over the place. For some of you it's challenging, for others it is not a problem at all. In fact, with respect to RapidMiner, the responses kind of goes from like, I'm never going to use it, why wasting time on this, to like, I know Python really well, I realize RapidMiner, I need to learn it, make me learn it, right? So there is like sort of the entire spectrum. Guys, one thing I can assure you, if you ever go and work for business, the further out, the less chances you'll be actually writing code in Python, or unless you're becoming a software engineer, the more chances you'll be using, either RapidMiner or, Alteryx, or maybe, Azure Machine Learning, but most likely it's going to be one of those visual programming tools you'll be working with. Now, this is probably, one of the interesting results where, we see how much time you spend. And again, this is self-reporting, so, you need to take it with a grain of salt, but still, probably on average around 10 hours spent on homeworks, which is, I think reasonable. What's surprising to me is the number of people who are actually using Python to do homeworks, which is 40%. Again, I guess for the next offering of the course, we need to think more about this and whether to provide, more flexibility in terms of programming language, or sort of go other way around and just say, okay, you know what, we'll level the field and everybody's using RapidMiner or some other software. But anyway, that's what we see right now. Again, as I said, we'll try to correct few things with lectures and with homeworks, see how it goes. You will have another chance to say what you think about the course at the end of the course. Okay? All right. So let's move on to the actual topic of today's today's lecture. What we're going to do, we're going to talk about customer relationship management. Well, in fact, pretty much, any company in the world deals with this, right? You often hear about CRM, but CRM being, software, but in fact, CRM is a process, right? It's the approach to managing companies' interaction with current customers and with potential customers. So it is really about customer acquisition, so getting new customers, and customer retention, making sure customers do not leave. Well, and keeping them happy in the process, because ultimately a happy customer means increased sales. There are a bunch of functions in the companies typically work with customer relational management. First of all, it's sales, the marketing, then there is usually customer service or support functions, all of them dealing with CRM systems and the CRM process, right? And again, the main part here is to keep you as a customer happy. Now, as I said, today, CRM is customer relational management is used everywhere in all kind of companies, but it's really the service sector that uses it the most. And for the service sector, this is the most important part, right? Because service sector is actually sector that or the industry that they do not produce any products, any goods. They provide services, and so their customers is literally their everything, right? And within with this type of services, it's usually quite competitive landscape, and it's for customer, it's easy to switch, so customer can easily leave to a competitor if there is a better offer, right? There are quite often quite high acquisition costs. So it costs you money to get new customer, whether, most of the time because, customers are taken. If you think about, I don't know, mobile market right now, MTS, Beeline, and Megaphone, right? They pretty much covers the entire market. And for any newcomer, they have to literally almost buy out customers from them, right? By providing either extremely better service, which is actually very hard because they will use the same hardware, the same network, or by dumping prices. Then it's repetitive interaction. When you think about service, again, mobile services, you're either on a plan which has to be renewed every year, and that's when people can leave, or again, like what happens in Russia, you can probably pay monthly, and so you can literally turn off or switch, disconnect once a month. Quite often for service companies, especially those that are interested in CRMs, there is quite large customer long-term value. So service sector industries, there are like a bunch of them, and you see this on the right, but it is really like telecommunications and financial services that are very, very competitive, aggressively competitive in terms of customer management, in terms of trying to retain the customer, trying to acquire the customers, right? And so for those industries like telecommunication, financial, the question of churn or customers leaving, right? They are very, very important, right? And in fact, for those industries, again, compared to, I don't know, retail, retail has a loyalty program, but the customer can shop today in one store, tomorrow another store, the day after tomorrow it comes back to you. When you get like telecommunication or financial services, if somebody leaves and start banking at the competitor, right, he takes money with him, and it's not an easy switch back. The same thing happens with mobile operators, and especially since in most of the countries you can actually take your phone number with you, people switch, and that brings a lot of losses to the operators. So because of that, telecoms and financial services paying a lot of attention to customer retention, and they're trying to they're running different programs, different marketing programs that tries to predict which customer is going to leave and provide them offers, such offers that they will be interested to stay. All right. And so when we talk about churn, telecom and financial services, these are sort of two industries where this is being used a lot. In general, the customer churn modeling is class of a problem that called propensity modeling. And propensity modeling is really the propensity or likelihood for a customer to acquire to buy a new service or product, right? It's a propensity to respond to an offer, and it is also propensity to leave, right? So it's likelihood for the customer to do something. Now, to efficiently interact with customers, because they have very different propensities of doing things, it's really good to understand and to be able to partition customers into those that have high propensity to say leave, to churn out, so medium and low, right? And the same thing with offers, and and suggesting offers. And then it's already after that it's a business decision, or whether you want to actually leave some customers alone and not waste your time and effort on them. And that could be customers either that are very much willing to buy a product, for example, because if somebody is willing to buy a product, you don't really need to waste your marketing money on this person. He's going to do it anyway. And maybe somebody who actually has very low propensity, you also don't want to waste your effort on those people because it will cost you a lot to convince them, and the probability that you're going to convince them is very low. So it's kind of waste, it's a wash. So maybe you need to focus on the sort of middle ground. So in any case, what you want to do is you want to be able to either, in the simplest way, to literally partition, right, all the customers into some groups with a certain level of propensity. And here is an example of like low, medium, or high. Or, which is even better, for each customer, compute certain score, which can be either probability that the customer is going to leave, if you can compute probability, and again, computing probability can be sometimes tricky, or it can be some sort of scoring system, some score, which is not necessarily the probability, but this score will allow you to kind of rank customers based on that score, and rank them, for example, from the highest probability of customer leaving to the lowest, and then you could focus your attention on the customers that are most likely to churn out, right? So two options again, like segment them, or maybe rank them, sort them, and then work on on the one side of this distribution. All right. So what we're going to do today is we're going to actually try to build that type of model, and in the homework, you'll be working and building the model for telecom operator churn prediction model. Okay, so we switch right now to the technical side, and let's talk about classification algorithms. Which we touched upon those algorithms in the previous lecture. I'm not going to go deep into the details how each of them work, but what we spend time on is understanding how to measure the quality and how to use them. So typically classification algorithms, you can either have a binary classification, classifying into two classes, or it can be multi-class classification algorithms, or you can use binary classification to classify into multiple classes by computing what's called one against all other classes. And what's really important that, in fact, the results of the classification algorithm, though we kind of use to have class assignment and class label as a result of the algorithm, very often the algorithm actually can or does return you the probability or some sort of score. And then there is literally, two-step process. The algorithm creates some score, and then there is some threshold set up, and based on that threshold, you can classify into different classes. And we're going to look into this. Now, examples of classification algorithm, the most probably well known is logistic regression, decision trees, and we use decision trees in the previous lectures when you worked with, I believe, with Titanic data set. Nearest neighbors, naive bayes, ensemble methods, which is a group of, say, for example, trees like random forest or gradient boosting trees, and the neural networks. So there's like many more algorithms you can list, but this is probably like the most popular. Couple things to point out. One is, if you remember algorithm we looked into when we did regression, they're pretty much the same algorithms, right? So all of those methods can easily be used in regression settings and computer regression. The other thing which is important to remember is that logistic regression, in spite of the word regression, is actually a classification algorithm, right? So that's like sort of usual confusion. But what it has in common with typical regression, it actually uses linear combination of factors, right? And so it's what's called linear separable. And in fact, if you look here, for this type of classes, this type of boundary straight line can be computed with logistic regression. You can also do it without algorithm, but this would be like a typical application. And if I look at this other picture, here logistic regression will not work too well because it will not allow us to have linear separation. And here, it's most likely you either do, nearest neighbors, or, ensemble method can actually help you do this, or there are other ways you can kind of transform the space and use it for classification. Now, let's go quickly. And again, I'm not going to go deep into the details, but just sort of to have this over a few algorithms, like logistic regression. Okay, so the problem set up, we have a target variable that we want to model. It's usually a binary class, 0 or 1. And we have predictors. Now, the same way as with linear regression or any other regression, here we expect predictors to be numerical, right? Be numbers. Now, if they're, instead of being numerical or categorical variables, we need somehow convert them into numerical variables. Sometimes it's easy to do, sometimes it makes sense, sometimes it doesn't make sense. So that kind of restricts where you can use logistic regression. And logistic regression literally tries to find parameters for this type of formula, where it actually calculates the probability of a particular data point belonging to a particular class. In this case, probability that our data point belongs to the class number 1. That probability is computed using the following formula, where you can see here a regression, right? It's a linear combination of different features. The goal of machine learning algorithm is to find those coefficients, beta 0, beta 1, etc. Okay? So ultimately, if I want to show this, this is probably the best visualization you can do for logistic regression. We can actually, since we have our class is a binary class, we can show the values on the x-axis. We can show variable if we think about one, if we think about single predictor variable, right? We can show on the y-axis probability, and then our sample data points are given here, and this is like the example of hours of studying and probability of passing the exam. And here is example of how many hours somebody studied, and the result is fail, because there is a binary result, you either pass or fail the exam. And then there is another sort of example of other students with certain number of hours studying, and the result, they pass the exam. So this is label 1. And what you do algorithmically, you actually try to, literally, I mean, you can think about this as interpolating between those two data sets, or you can match this probability function to those two data sets. And that's sigmoid function, logistic regression function, and the way it's mapped. The way to read this is that if you study 2 hours, probability to pass the test is 25%. If you study 3 hours, probability to pass the test 60%. If you study more than 5 hours, well, it's almost 1. right? So very simple, very intuitive. And the key here is that it actually returns probabilities, okay? All right, so that's logistic regression in a nutshell. You know, I kind of refer you to textbooks to understand how those coefficients are computed if you want to, right? For us, what's important is what's in and what's out. So we get variables in, we get probability out. Okay, so next is decision tree. And the decision tree is sort of the most, probably the most intuitive algorithm you can have out there, which is literally just a set of rules where you have nodes that are internal to the tree. Those nodes are decision nodes where you have if-then statements, right? Where you make certain comparison with respect to attributes. And then you have leaf nodes, which are outcomes of classification. You know, in this case, the target variable, if we're talking about classification, can be the binary class or multi-class, or in fact, you know, can be regression. If the target is, you know, actual value. Predictors can be numerical or categorical. The tree doesn't care, which is actually a very, very big advantage of trees, that you can easily mix and match numerical and categorical variables, and it does not hamper the behavior of a tree. And as a result, eventually you get you know, different leaves, and you know, this is a tree. When you get a new data point that you need to evaluate, you know, it goes through the tree based on the rules. And here is, for example, the rule says glucose is less than, you know, whatever entropy, and then there is entropy and number of samples, that sort of the information about how the tree was built. And then there is BMI index, and then age, and then you end up in class 0, for example, right? Now, that's a tree, right? And in some sense, when you just look at the tree, you know, every leaf gives you a class. And so when you sort your example through the tree, well, I mean, when the algorithm sorts your example through the tree, when you do evaluation, it assigns a class value, right? So you're becoming either class 0 or class 1. All right. Now, what's interesting is that when you build a tree and you build those leaf nodes, very often, and actually this is the right way to build a tree, you don't leave one training example in the leaf node. There are multiple of examples that remains in each leaf node. And so the leaf nodes, they're not pure. And if they're not pure, when you classify a new example into that node, into that leaf node, you can actually also think about probability of that example belonging to the particular class. So for example, you know, if you classify your green point into this, if it ends up in this bucket, in this leaf node, yes, the probability of being green is 1. But if based on this split, it ends up in this leaf, the probability of being green is 1/2, right? Or if it ends up in here, the probability of being yellow is 3/4, green 1/4. So it also actually returns us certain type of probability for an item, for a sample belonging to a class. All right. Now you will see why I'm talking about the probabilities or scores. What I really need for the further discussion is that the classifiers, for us to understand that classifiers in fact return scores. Okay. Next one, random forest. Now this is sort of a workhorse for, you know, for algorithms. Literally, you know, if you try something very simple like logistic regression, you know, it doesn't work, you can go for decision tree. I mean, sometimes yes, sometimes no, and then you just go and do like random forest or gradient boosting trees. And that's independent of whether you're going to do, you know, regression or classification. So here, again, sort of very, very sort of top level, the idea of random forest is that instead of one tree, you have multiple trees. Now you want to make sure those trees are different, right? They're not the same. And so when you build those trees, what happens is you sample your data points when you build them, and you use what's called bootstrap sampling. And then also each tree uses sub-sample of features, so it doesn't use all the features. And then what you do is a sort of committee, right? You have a bunch of trees. Each tree gives you a class for an item when you send it through, and then you vote for a class, and then they vote for the class. And so this really means, you know, if for example, you send an item through all those trees, and trees sort of, you know, disagree, right? Tree number 1 says it's class C, tree number 2 class D, tree number 3 says class B, tree number 4 class C. Well, you know, you can actually, as a result, yes, you can do the majority voting and say, this is an example of class C, or you can say, look, there is a 50% probability that this is class C, there is 25 that's class D, and 25 that's class B, all right? Now, you can actually make it even more complicated. As we discussed previously, you can actually also take into account that each tree does not have to return a particular class, but can also, you know, being on the using the purity of each leaf, also return probabilities. So bottom line, random forest, also ranking algorithm, or scoring, ranking or scoring algorithm. Okay. So one other important point here is there is no difference in between you know, the classification and regression algorithms in terms of you know, how you actually train and test them. So as the same way as we discussed before, you know, you split into train and test data, and you know, the usual rule will be that on the trained data set, the quality will be, you know, better than on the test data set, right? The question is the only question we have is you know, how to compute this prediction error, because if you remember, for you know, for the regression, it's just sort of misfit, right? You know, we looked at you know, standard deviation, right, at RMSN error. Here, we're going to talk about this right now in a couple of minutes, what we're going to use as an error. The other important point here, and we didn't talk about this, but it's important, and this is also important for us. When you split into training data and test data, you know, test data is what stays untouched. Now, within training data, you can actually, you know, subdivide the training data into, you know, pieces, and you can think about, you know, dividing this training data again even more into train and sort of more kind of local tests, so that you can, in fact, adjust parameters of your models, right? Now, typically, this division is done through what's called, you know, cross validation, right? Multifold, and then you kind of reuse this training data multiple times, right? You know, why is this important? Well, because you know, a lot of algorithms, you know, out of the box will give you some sort of quality, but if you want to improve that, you know, you might want to, you know, adjust parameters. And I know in the seminars you discuss the grid search. So grid search works within this framework, where you go through different parameter settings, and say in trees that could be, for example, the depth of the trees, and if it's random forest, say the number of the trees, and you find the optimal value. But then whatever result you got on the training data, it is on the training data. Then you need to run it on the test data that you have not touched and you have not used to adjust your parameters, right? That's the key here. You know, it has to be kosher. All right, so that's model training and testing. You know, again, it does matter whether it is regression or classification, right? It's the same process. Now, the only question is, with classification, what's prediction error? Because that's like the key here, like what we're going to use for prediction error. And what we're going to talk now is, in fact, probably one of the trickiest topics out there with classification, right? So I'm not going to rush through it. Let me know if it's not clear, because that's like sort of the key to good classification. Now, on the previous lecture, we discussed the options, the results of the classification, right? And when we have a classification, if we have binary classes, for example, we have very simple matrix, confusion matrix, right? If it is more than 2 classes, well, the matrix will be bigger, but the idea is that there are actual values, positive and negatives, and then they are predicted. And if the actual value is positive and what I predicted is also positive, I call it true positive. False, if the actual value is negative and I predict that's going to be positive, it's false positive, etc. And then we said, like, look, there is this metric, accuracy, right? That in general can be used to evaluate classification quality. And that metric says, look, we just calculate how many times you're right in terms of predicting positive values, how many times you're right when you're predicting negative values, which means how many times you correctly predict this class and the other class. And that sort of ratio gives us the quality of the algorithm. Well, the point being, this is not exactly true. The reason you will see in a second why accuracy by itself is not a good metric if just used by itself. So you can calculate it on a particular data set, but if you want to compare the performance of the algorithm between different data sets, or if your data sets have slightly different distribution of true positive and of positive and negatives, and that might happen when you do sampling, then accuracy will not be a appropriate metric. Okay. Let's see why this is, why this is true and why we need to pay more attention to this. Look, imagine that you have an algorithm that has 80% accuracy, right? You're telling me, I have this excellent algorithm which is 80% accuracy. So the question is it a good algorithm or not? I mean, 80 sounds like a good number, right? Now let's look at this. Imagine that you have a data set that consists of 50% positive examples and 50% negative examples, which means half of the students are going to pass the test, half of the students did not, right? So my historical data shows that 50% of the class failed, 50% passed, right? Now, if that's the case, I can, for example, use what's called majority class classifier. So majority class classifier is this brute force idea where I will assign to every point the value, the label of majority class. So since there's 50-50, well, okay, let's say it's 51 positive and 49 negative. Let's say I assign everything positive, right? In this case, out of 100 students, how many mistakes will I make? So there are 100 students, and I'll say I know that the distribution is 50-50. There are 50 that failed. There are 50 that passed, and I'm proposing an algorithm that just says everybody's going to pass. What is the accuracy of this algorithm?
0.5.
It's 0.5, right? It's 50%, because I will miss half of the data points. Now, if you're giving me an algorithm, proposing me an algorithm that provides accuracy 80%, it's better than mine, right? Okay, make sense? All right, now let me give you a different class. Let's say this is a better class, and in this class, there are, it's a stronger class, stronger students, there are 90% of those students pass exam and 10% fail, you know, in last year, right? And I'm training on the last year to predict what's going to be happening this year. What I'm going to do is I'm going to create what I call majority class classifier, which is you give me any student and I'll give it a label that he's going to pass. All right? Every student, I'll say they pass. So it's dumb classifier. It just says pass. What error will it shows on this data set? What's accuracy?
90%.
90%. So all of a sudden, your algorithm that gives me 80% accuracy doesn't look good anymore, right? Okay, so that tells me that I need to, when I talk about accuracy, I need to talk about the data sets, right? I need to talk about the balancing of the classes in the data set. By itself, accuracy is not going to do it for us. And that's very important. It's also very important because if you train just on accuracy, and you know, last year we expected this kind of ratio of positive to negatives, and this year distribution shifted, it's not going to work well. So accuracy by itself is not a good metric to determine the algorithm quality, classification algorithm. So what can we do? I mean, the answer is sort of, you know, the answer is obvious and easy, but it kind of can get complicated because, you know, you need to take things into account. So it's clear what's important is this ratio of positive and negative. And so the solution to the problem with a classifier is, instead of actually calculating and using, you know, true positive or false negatives themselves, what you can do is you can do a ratio of number of true positives to the total positives in your sample, and negatives to the total positive in the sample. And again, this is actual, right? This is actual, you know those things. This is what your algorithm predict. And the same with negatives. All right? So number of true positives plus false negatives is the total number of positives. Number of false positives plus true negatives, total number of negatives. So what we're proposing to do is, instead of using true positives, you take this and you divide it by this plus that, right? By the total number of positives. Now, I mean, it's called a confusion matrix. It's not supposed to be confusing. It is getting confusing when you start like dividing things here, and there are like a lot of questions. And it's, in fact, it's easier for yourself to try those things than me, you know, explaining the formulas. So I strongly recommend you trying those, because they're quite obvious, but it takes time to get used to them. So bottom line, what I'm saying is, instead of characterizing your algorithm by accuracy, you need to introduce, because accuracy depends on the balance of positive and negatives in your data set, you need to use the relative metrics. And the relative metrics is called, for example, true positive rate, which is true positive divided by the total number of positives in the class. And false positive rate, for example, which is the false positives divided by the total number of negatives. Now, there are four numbers here, right? There are four corners, four variables, four numbers. But because true positive plus false negatives gives us total positives, those two numbers, they are related. And so if I know true positive rate, which is this one, I can calculate this one as 1 minus true positive rate. Since I know this one, for example, I can compute this one as 1 minus that. All right? So the only thing I'm doing is I'm normalizing. But this normalization instantly removes the problem with accuracy. And you know, here I try to show why it is so. You know, just bear with me. accuracy is true positive plus true negative divided by all positives plus negatives. I can decompose this, and then what you'll see is accuracy is a combination of true positive rate times the fraction of positives in your class, in your training set, plus 1 minus false positive rate times the fraction of negatives. So these two ratios, this one and this one, depends on your data set. This number and this number is a property of the trained algorithm. So accuracy will change if your training and test set have different ratio of positive and negative examples in them, or if you're just running on a different data sets. But true positive rates and false positive rates, they're property of algorithm, they will not. Okay? So, bottom line, after all this sort of long story, make it short. If I want to evaluate the quality of the algorithm, which is a classification, using accuracy is dangerous. You can do it, people do it, but you need to be aware that the accuracy depends on the ratio of positive and negatives. If somebody says, my algorithm, hey, we built this cool algorithm, you know, it is 85% accuracy, the only question you need to ask is this person to understand, if he understands what the heck he's actually telling, is, and what's the ratio of positive and negative example in your data set? If he does know, those numbers are bogus because they don't make any sense without, without that value, okay? All right, and any questions here? Let me pause because it was quite intense. Let me pause here, see if there are questions.
I actually have a question, not about like this classification and something. I have a question about logistic regression and decision trees. So basically, for example, we had this homework with Titanic data. So in principle, we could use both algorithms. So what is the advantage of one and disadvantage of the other, and in which situations one algorithm is preferred to another one?
You know, I will let later on at the seminar on VAR to go deeper into this, but some of the obvious advantages is if your data points, let's say you project your data points onto you know, 2 dimensions, and if they're linearly separable, right, then, you know, logistic regression can do it. Decision tree can also do it. It might be a little harder for the decision tree, but they can do it. Now, if your picture is like that, which more likely, that might not be happening easily. You know, for logistic regression, there is no good sort of separating line. At the same time, also for trees, as I said, you can easily use very different features, right? You can use age, you can use the class of the service, you can use port of loading, you can use, I don't know what else in there, I forgot. I mean, you can use all of those features. In logistic regression, if you think about this, you're actually building a linear combination out of them, right? So you need to somehow convert, for example, you know, you're adding age and the port of loading, right? Which might make sense, might not make. So you need to somehow convert those categorical features into numbers. Or for example, if you use, you know, the class of service 1, 2, 3, you just cannot put here 1, 2, 3. You can do like one-hot encoding because, I mean, the 1, 2, 3 do not make sense because, you know, the way the regression works, right? So there are different classes. These are not just numbers. So logistic regression requires care when you deal with it in those type of situations, all right? But having said that, there are also algorithms where, for example, leaf nodes, what you do is you put a bunch of samples, you leave a lot of samples in the leaf nodes, and then you build regression per logistic regression kind of thing in each leaf node, because you have several samples there and you can still separate them. So, you know, both algorithms have a usage. Again, typical advice in practice, you start with the simplest thing, which is like logistic regression or regression. And then you make it more complicated. You know, you can go through trees, or you can just go right away to ensemble methods. All right, guys, let me get back to this, because this is like critically important part. So we have, as I said, accuracy by itself is not good enough. You need to use the true positive rate, false positive rate. Now, in fact, classifiers can be distinguished, differentiated, plotted on this diagram, where on one axis you have false positive rate, on the other axis you have true positive rate. And different classifiers, having differently, they're differently trained, they might have different rates, right? So again, what's true positive rate? True positive rate means instant is positive, and the algorithm says, you know, yes, it is positive. So it's percentile of positive detected items in the sample. Let's think about this as a problem of, testing, or let's say it is a system that it's an entrance control system, right? So we are actually allowing an entrance it's automated, face recognition system that allows somebody to enter the home, right? Enter the building, security. So what this says is, it says positive, right? So it really says that it detects 40% of positives. So if you have 10 people, 4 of them will be able to enter. 6, though they have a permission to enter, but the system will not detect them. And so this is what's true positive here. Or if it is, if there is a fire, well, it detects a fire, right? And it says, yeah, it's going to be a fire. It is a fire. Now, false positive rate is false alarms. It's when, nothing actually happens, but the system detects it. So again, let's look at this. This classifier, classifier A, has, true positive rate 0.4 and false positive rate, false positive rate, here it's 0.08, right? So it's a small one. So what does it mean? It means it has very low false alarms. And it has, but it does not have, very good true positive, but it is still pretty good. Now, if you have a perfect algorithm, right? Magic. It will always detect all positives. It will never create false alarms. Think about the alarm on your car, or on a car. It never just sounds unless the car is being stolen. Think about fire alarm that is only triggered by a fire, never ever misses a fire, and never ever sounds if there is no fire. We're here, right? Now, that doesn't happen in real life. What usually happens is you either have a very sensitive alarm that can work and that will be triggered in most cases when the fire happens. It maybe misses, 5% of fires. But it also has pretty high false positive rate, which means it's going to be triggered if somebody, smokes a cigarette or switches on the lighter. Okay? Or you can work here, where you kind of crank down the sensitivity. You might be able, you will be missing the real fires a lot, right? You'll be able to detect only 40% of real fires, but it will not wake up in the middle of the night because it's not going to be creating false alarms. So pretty much all the algorithms, all the classifiers, they live somewhere here. Now, this diagonal is kind of funny diagonal. On this diagonal, your false positive rate is equal to, your true positive rate is equal to your to your false positive rate, and that's random. That's sort of the random algorithm. That's when you flip a coin. So any algorithm that has performance here, it's useless. It's just random guessing. Any algorithm that is below, it's actually inverted. It usually mixes up classes. If you end up here, check your classes. You probably mix up, you call positive what's negative and other way around. So this is the working space for your algorithm. Pretty much any algorithm that you create, you train, will live somewhere here. If it's perfect, it's going to be here. If it sucks, it's going to be here, along this line. All right? So any algorithm has a place on this chart. Make sense? All right. Oh man, we don't have that much time. Now, what's also interesting is this, and this is called, by the way, ROC space. It has a name. It's called receiver operating curve. And we're going to talk about it right now. So what I want to show that any algorithm, the one that we have all those ranking algorithms, they can be represented on this diagram with this line, and they can operate at the different levels of true positive, false positive, true positive, false positive. Now, why is this true? Well, because what you're trying to do is you try to take an algorithm and change the sensitivity of the algorithm. By changing the sensitivity of algorithm, you kind of increasing the number of positive signals it can identify, but you're also increasing the amount of noise. So let me try to explain this on this scoring thing. And remember, I started the lecture talking about scoring, right? I said, look, scoring is important. Our algorithm creates scores. Scores, we need scores, scores, scores. Here is why. Let's say I have an algorithm, and then I ran my test set through the algorithm. And for the test set, I do know the classes that the items belong to. Say it's positive and negative. And my algorithm creates either probability for an element, an item to belong to the class, or some score that the higher the score, the more chances it belongs to that class. So then what I do is I sort, I rank all my samples based on the score. I just sort them. All right. Then what I can do is I can do the following. I can put a threshold somewhere. And I can count how many times the algorithm made a mistake and how many times it was correct. So I can put a threshold and say, look, everything that is positive is under this threshold. Everything that is negative is above the threshold. So I'm saying everything below the threshold here is positive, and above the threshold, all the elements are negative. So I'll be sorting it into those classes. Then when I move the threshold, the elements will fall into one class or another. Some of them were at the beginning, maybe in the positive, they will actually be moved to the negative class. So here is how it works. We start, I start with a threshold. Well, if I put it like above 0.99, I don't put any elements, any samples in the positive class. It is 0. I move the threshold right here. Well, there is one element which I consider positive, and its true class is positive, so I put it here. I move my threshold one more time, right here. I got another element here. It's positive. The true class is positive. I increase the count. I move the threshold even more, above this value. But guess what? There is a negative here. The algorithm somehow put a negative there, example. So algorithm made a mistake. Okay, so I increase count of the mistakes. And so on and so forth. You just keep sliding this and creating new and new confusion matrices. So depending on where you put your threshold, your algorithm will produce different quality solution in terms of the false positive and true positive rate. And so by moving the threshold, I'm slowly moving along this line, and your algorithm is actually represented by this line. And every point here corresponds to a particular level of the threshold here and particular confusion matrix. All right. I pause here for those of you who complained that the lectures were too light. I hope this will give you something to think about. But this is sort of in depth how we actually use classification, right? So step one, your algorithms are ranking, so you can rank elements. Step two, you choose a threshold. Now, let me quickly move this into the practical realm. What these items are your customers. What you do is you score all your customers, and depending on the score, you rank them. You believe that these customers are those who are going to churn, right? You know that the customers that at this end, they're going to stay. And then you can say, look, if I put my threshold somewhere in here, I'm believing my algorithm thinks that these are going to be churners. This is going to be non-churners. If I say that these are churners, I'm making some mistakes. I checked it right now. There is this 2 guys that says no. So I made, two mistakes here, but the rest are positives, right? So this assumes, of course, that, when you train algorithm, the ranking is not just random, right? The ranking gives us, the ranking is such that the closer you are to this side, the more sort of positive examples are in there.
Leonid, may I ask a question, please?
Yes.
When you say, when I put the threshold or when I move the threshold, do you mean that it is, you set the hyperparameter, just manually set that a threshold, or algorithm itself decides that threshold?
I'm sorry, could you please, there is noise here. Could you please repeat your question? I just couldn't hear it. Could you please repeat it?
Is it good now?
Yeah, is it good? Yeah, it is. Thank you.
So the question is, when you say, when I move the threshold or when I put the threshold, do you mean that you set it like a hyperparameter, you set it manually, or it is calculated by the algorithm and it is just the algorithm decides where to put the threshold?
Very good question. So, I mean, I think this is a question which, half of the people who we interview for like data scientist position fail. The question is, literally what you're asking is the following. If you have this curve, where along this curve I want my algorithm to work, right? Or how to choose this threshold, right? And a lot of people, by some reason, say, well, we put it at the 50%, right? We'll say, you know, half, you know, let's say it's from 1 to, you know, from 0 to 1. Well, I'll make it 0.5, and, you know, whenever 0.5, I put a threshold. That's the wrong answer. The right answer is the following. Depending, you know, these numbers are not just numbers, right? These are customers. And when our algorithm making mistakes, we're making mistakes regarding this customer's behavior. Now, depending on what we predict, we're going to spend some money on each of those customers, right? We're going to pay them, give them discount. And we're going to waste money, or we're going to make money. So what you can do is, depending on the cost associated with each of those numbers, you can actually calculate the optimal position of this line such that you'll have maximum profit. One more time. Changing position of this line, you change the prediction quality of your algorithm. If you're right here, your algorithm is very, very pure. You know, it gives you very good quality, but it will also tell you that there is these 2 guys that are going to, you know, leave, or there's 1 guy that's going to churn out. Yes, you're right. There's only 1 guy that churn out, according to your algorithm, and the guy will churn out. So you give him discount, he will stay. But then you missed like 99% of everybody else. Now, if you put your line somewhere here, you actually will have to give discount to all these guys. Giving discount to these guys might be a good idea, but there are some of them that do not need discount because they were not planning to leave. So you wasted money on them. So the question is, you can position this such a way that you will optimize you know, your profit overall when you look at all the customers. Does this make sense? Guys?
Thank you.
Yeah, okay, good. Actually, on the next slide, we're going to do this. So the answer
one more
is,
question, sorry.
Yes.
How we can apply this approach to multi-class classifier?
Usually, okay, there are ways to generalize it. Quite often you do like 1 against all, right? So when you do multi-class classifier, there are 2 ways to do it. You just do it like into multi-classes, or you can say there is this class, like say you have 3 classes. You do this class versus 2 and 3. Okay. All right, guys. Now, this is typical, you know, receiver operating curve. We're almost out of time. The most interesting part here, this is a real one now that you can build. And the quality of your algorithm is measured actually by what's called area under the curve. We don't have a lot of time to actually, for me to explain why this is true. But as we discussed, the perfect algorithm is right there. The real algorithms are usually, you know, can be here, 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 here. So the classifier, your classifier can operate anywhere along this line, or, you know, this line. So the quality of classifier then is measured. We want to measure, you know, this line, and we know that, for example, this line, oops, oh, fine, overall is better than yellow, and, you know, if classifier can operate along this line, it's even better. So the way to compare those lines is by the area under them. And so that's why there is this metric which is called ROC-AUC, or end area under this receiver operating curve. And you know, if your curve were like this, that would be perfect. And then ROC-AUC is 1. And if it is, as we discussed, you know, random, it's diagonal, this ROC-AUC is 0.5, which is bad. So the closer your ROC-AUC to 1, the better is your algorithm. bottom line of this our discussion. If we're talking about the quality of algorithms, we are not looking at the accuracy in classification. We're looking at this metric, area under the curve, and that's a single number that will tell you how well your algorithm performs, and that number does not depend on the ratio of positive and negative examples in your data set. All right, I need to go and do a couple more slides before we're done today because they are important for the homework. And you know, we're going to cover them. This ROC, AUC, like receiver operating curve, this is a terminology used by data scientists. Business people don't usually know it and do not understand it. But what they do understand is what's called lift curve. Let me introduce those two curves that actually can be easily derived from this REC curve. One of them called cumulative response curve, another is called lift curve. So the idea is the following. Remember this picture, right? So what we can do is we rank all the customers, and then we start, you know, cutting, putting a threshold, and we're saying, you know, these are all positives, these are all negatives. You know, we can move threshold again and say now these are all positives, these are all negatives. So as we move threshold further along the score, we're actually covering more and more and more customers, right? So this is the motion, you know, this way. We're covering more and more and more. What you see here is how many, relatively speaking, positives we're picking up. Now, what's extremely important, if your ranking, if this ranking scoring does not work, then the ordering of these guys of positive and negatives will be random if the ranking doesn't work. If it is random, and then I cut, say, I pick up, you know, 10% of my customers here, how many positives do I expect in there? The same way as across the entire data set, which is 10%. I cut at, you know, 50%, I expect 50% positives to be there. So that corresponds to this line. What you see here is the result of ranking, which says that the closer you are to 1, right? The closer you're here to the bottom, the more frequently you got those positives. The more frequently there were more positives here. Now, when you get to all 100%, all positives will be in there, but you covered 100% of people. So the way to understand this is the following. If I use my ranking and pick up 20%, let me clear this. So if I use the ranking, and based on the ranking, I draw it, you know, somewhere here, and let's say this picks up 20% of all population, then if I didn't use my algorithm and I just take 20% customers, I will get 20% churners, not because they're all distributed among customers, right? I take 20%, you know, there are 20% in there. But if I use my ranking and pick up those 20% from, you know, the top of the ranking list, I will actually collect 50% of all churners because they kind of, you know, concentrated in there. And if I take 40%, top 40%, I'll get, you know, almost 80% of all churners. If I didn't do the ranking and I just randomly pick up 40% of the customers, I would get only 40% churners. But because I did the ranking, now picking up 40% customers, based on the ranks, I'll get 80% churners. Does this make sense? Okay. Now, this is called cumulative response curve. The lift curve is just the ratio of this over there doing nothing. So this is how many times better is my algorithm over doing nothing. So if I take 20% of customers, then lift here for 20% is almost 3. So I'm almost 3 times better in terms of selecting customers than just randomly picking them up. If I take top 10, I'm even 4 times better than randomly. If I take 40%, I'm 2% overall better than random, right? So this ranking allows you to concentrate customers you're looking for, at the, if you wish, at the top of this list, right, or bottom of the list, however we call it. Okay. Now the challenge of doing this lecture online, because if we're in the audio, in the university, I could stop and ask and look at your eyes and see if it makes any sense or not. Now I cannot do it, right? I see that I lost pretty much a lot of people in terms of videos. So we might. We'll go over this a couple more times because this is probably the most critical part, in all sort of modeling for supervised learning. It's not easy if you never heard about this, but this is sort of the key to the usage of supervised learning for this type of problems. So again, what you do is you have 2 types of classes. You have people who respond to the offers or not. You have people who who will churn and those who will not. Based on those 2 classes, you can train classifier that will allow you to rank all the people by the likelihood of churning, maybe probability, maybe likelihood, so giving them the risk score. Then taking that risk score, you can sort the people by that risk score, and then if you take the people with very high risk score, right, you'll cover a lot of people who will churn. You'll take more, the density of those churners within that segment will decrease and decrease and decrease, and that's what's shown in the lift curve. Now, very last slide that we need. Actually, 3 more slides. Shit. Okay, so customer churn modeling. What do we do? In the customer churn modeling, this is a customer flow. So we have new customers that we get, and these are sort of active customers that are using our service that we make money off. Then we try to use our model because we want to understand which of these customers are going to stay with us and which can churn out. So churn model gives us, remember confusion matrix, right? Gives us classes. We have predicted churners and we have predicted not churners. Among those predicted churners, there are true positives, which are actually going to churn out. Then there are false positives, which our algorithm thinks that they're going to churn, but they're not, right? Then there are predictive non-churners. Some of them will churn out because algorithm is wrong. And then there are non-churners that we predicted they're not going to churn and they will not churn. So these are our predictions, and then actual non-churners will not churn and go back to become, staying customers for the next time. These guys, these are actual churners that will churn. We predicted that they're not going to churn, so we made a mistake, which means we're not going to do anything about them, and they will churn, they will leave. These are our mistake, we missed them. Now, Then there are actual non-churners. We said they're non-churners and they're not churners, and so we don't do anything about them. They come back, you know, they're customers. And then there are actual churners. Now with actual churners, we can give them some discount, but they might take it or not. If they take it, let's say, you know, there is say gamma percent of them actually accepting discount and coming back, I mean, staying with our service. And then there is another fraction that will live. So that's our churn model that we're going to work with. So how do you, from that, how do you go back to you know, the sort of the profit, right? The discussion of how or where to put that threshold. So here's how you do it. It's called you know, cost-sensitive learning, or one of the version of a cost-sensitive learning. So what we have is we have our you know, confusion matrix, and we can calculate all those expected rates as we learn how to do. You know, true positive, false negative, true negative. These are the rates that we computed from you know, confusion matrix, right? So that's sort of the rates that we get. On top of it, we need to create what's called cost-benefit matrix. And the cost-benefit matrix tells us what's going to be benefit or the cost for the particular prediction. So if we predict that somebody is going to stay and the person, I'm sorry, in this case, positive is churning, right? That the customer is going to churn and the customer is going to churn. Then what we can do is, if we can predict that they're going to churn and they will, and they're actually churning, right? We can give them discount and they will stay. So then we are making profit by having these customers for another, you know, say a year or another time period, minus the cost, which it costs, minus the cost that, you know, minus the money that we spent on that offer. If we are predicting that somebody's going to churn, but they're not going to churn, then we're wasting money, because if we're predicting they're going to churn, we're giving them money, they'll take it, right? But they were not planning to churn anyway. So we're not gaining anything. These guys are just taking money. So that's where algorithm wasting, you know, resources. If we say that somebody's not going to churn, you know, we're not doing anything. So this, for us, this is, those two things not important. But in other models, they might be. So we can calculate expected profit, and expected profit will be the cost of each sort of action, each scenario, times you know, the rate, right? The probability of that scenario. And if we're working with expected rates, right, with true positive, false positive, we also need to multiply this by the probability of that class, right? Remember that class balance, class distribution. It's important here because usually the classes here are quite unbalanced, because the number of churners is usually, you know, several times smaller than the number of non-churners. So then you put all these things together. And as a result, you got the following. Again, let's say you select, you have the ROC curve, right, for your classifier. You build it, you have it. Now the question is where to draw this line, right? Draw it here, draw it there, draw it there. So where to put the threshold? So what you do is the following. So for every threshold position, you do have your confusion matrix with the rates. Then there is this economic data, and that's what we'll provide you. You cannot extract it from the data set itself. It is how much it costs you, how much revenue you get per customer, and how much it costs you to give an offer, right? So here, an offer is, $10 per customer, and total, revenue is $100. Say 100 minus 10 is $90 profit. And so and then you just multiply and you get a number. And then as you change the position of the threshold or go along this line, you will actually calculate, you'll get different profits. And so you can actually find out the optimal position of the line that maximizes the profit. Now, if you use different classifiers.
I'm sorry. Question is, you were referencing to a time that we are going to retain this customer for a determined period of time. Is it another variable that you have to somehow predict, because it is not the same in terms of profits if you are going to retain the customer for 12 months or if you are going to retain it for 6 months?
Yeah, that's a good point. The way, sort of in real life, yes, you actually build different models for, retaining for 1 month, for 3 months, for 2 months, for 3, et cetera, because expected profit will be, of course, monthly times number of months. But then you also train it slightly differently. So what, the way we specify it here will fix, I believe we're going to give you, just sort of one-time interval, so you don't care about timing here. It is, there is this history of the behavior, then there is a fact that customer left or not, and then we need to predict for other customers whether they're going to leave or not, right? But in real life, you're absolutely correct. You actually, train this, build the set of models for different time horizons, and you also retrain them because the behavior of the customers does change with time significantly. Like right now, we have a crisis situation. There is very different dynamics. In fact, most of the machine learning models failing right now. They have to be retrained because the behavior is different. Anyway, guys, so that's the point. Now, pretty much all this is, I followed quite closely in this lecture the book Data Science for Business, right? That the one that we have, the one that I recommend for the course. There are a couple chapters about this. So I do recommend you read through them, because this is really like the core of how we use machine learning in business, right? We're way over time. So thanks, and we're gonna start the seminar in a couple minutes.
Sorry, I have a question.
Yes.
If we swap positive and negative class, our ROC curve should be slightly changed, yes? But what about AUG? Is it will be same or not?
It should be the same.
AUG.
If you have binary classifier, it doesn't matter whether you class what if you call one positive, another negative. It's symmetric.
But ROC curve should be different.
No, what I meant is if you, for example, train it in the wrong way, right, mixing positive and negative, it can actually flip and be sort of underneath the diagonal, right? If you, for example, call positive and negative class another way, and in training and in testing, you mix them up.
No, I don't speak about mixing. I speak about like just swap what we call positive and what we call negative class. I mean, actually, we can calculate two ROC curve when we suppose our, I don't know, that some people buy it, it's positive class, it's not buy it, it's negative. If we say, so okay, positive class, it is people not buy, and the negative class, it's people will be buy. So our curve should be a change, but it also will be like good if we have a good classifier. But what about AUG?
I think AUG should stay the same. I mean, just from the symmetry of the problem, because if you can change it you know, without losing anything, right? Just flipping, literally flipping zeros and ones right here. If you change without losing anything, there is no reason. You're not adding any information or removing any information. So just from this general kind of statement, there shouldn't be any change. So the quality should remain the same. It doesn't matter what you call positive, what you call negative.
Okay, thank you.
All right. All right, guys, thanks. Please switch to another channel.
Okay, thank you.
Thank you. Bye.
Thank you very much.
Thank you. Thank you.
Thank you.